Kf is 2 Kelvin kg per mole, right? And what is the value of T1 and T2? A difference, right? You need to tell me the difference.
So we have to find the formula delta T is equal to M into Kf, right?
Yeah, right. Exactly. The freezing point depression delta Tf will be equal to Kf into molarity.
So what is the formula for urea?
What is the formula for urea? Yeah, urea is a very important compound. It is NH2CONH2. Right? So its molar mass is how much you are getting? Tell me quickly. Molar mass of urea. You can remember it because it is very common and it is being asked every time.
Sir, is it 16?
Yeah, it is 60 gram per mole, right? Yeah. So it is 60 gram per mole. How many moles you have taken? That you can tell me. In the question you have taken 0.1 mole, right? 0.1 mole per kg. So molarity is going to be directly, it is going to be 0.1. Delta TF, that is going to be 0.2. Okay. So the depression in freezing point, that is going to be 0.2. Okay. So the depression in freezing point, right? That is going to be 0.2. Okay. Clear?
Yes, sir.
So let's move to the next question. Let's discuss it. So what is the difference? So the depression is 0.2, but what is asked? So that this is delta TF, but you need to know what is asked. Are they asking T1 minus T2 or T2 minus T1? So accordingly, you need to answer. Okay. So 0.2 is the difference. Okay, but if they may ask that what is the difference T1 minus T2. Okay, T1 is higher and T2 is lower, so that is going to be positive. Okay, and if they ask you T2 minus T1, right, that is going to be that could be negative. Okay, clear? So yeah, let's move to the next problem. This is the next problem. So tell me, how can we do this problem? Yeah. Mehraj, can you hear my sound?
Yes, sir, I can.
Yeah, good. So we were discussing last time freezing point depression, and there was some just we discussed the theory. Okay, if you remember. So we need to do some questions. So just this is the second question. The first question was very easy. I was discussing with Samara. So let's do this. So 2 grams of an unknown compound reduces the freezing point of 75 grams of benzene from 5.53 to 4.9 degrees Celsius. Okay, what is the molar mass of the compound? So this is the basic type of question which we can expect in any examination. Okay? And this is the purpose of studying freezing point depression. Okay. Clear?
Sir, send the answers.
How much is the answer?
Sir, C, sir.
C. Okay, molar mass.
Yes,
And
sir.
Samira, what you are getting? Let's check it quickly. So it is the how many moles of that unknown compound you took. Let's its molar mass be m, so 2 gram by m. Okay, and you molality is mole per kg of solvent. Okay, but the solvent which you took is benzene, but that is only 75 grams, as you can see. So what you need? Okay, you need to divide it by 1,000 to make it kilogram. Okay, but this is the molality. And what is the value of Kf? For benzene, we need 5.12, and the freezing point depression, that is 5.53 minus 4.90, it is going to be 3, and this is going to be 6.63, right? Samara, what you are getting? Mehraj is getting option C. Okay. Yeah. So you can solve it. This and the data is also very good data, and you can cancel it very easily. And the right answer is option C. Is it clear? So the same way. So I hope you are getting right.
Yes, sir.
Yes, sir.
Okay, good. So let's move to the next question, and the next question is yeah, that is freezing point depression. Let's do it. The solution of urea boils at aqueous solution of urea boils at 100.18 degrees at atmospheric pressure. If Kf and Kb of water are 1.86 and 0.51. So boiling point is given. You need to tell me the freezing point of this urea solution, which is given in the question. Okay. Yeah. So question I hope is very easy, and you can do it very quickly. Yeah, good question. So boiling point is given. You need to tell me the freezing point. Yeah.
Let's send the
What is the answer?
sir. For me, it's coming D.
D. Last option.
Yes, sir.
Okay. And Samira, what you are getting?
So can you explain this question?
Yeah, this is so delta T B is equal to kg into molality. That we know. Similarly, delta Tf is equal to molar cryoscopic constant, that is Kf into molality, right? We can divide them, okay, and we will get delta Tb by delta Tf equal to Kb by Kf. And as you can see in the question, okay, you can see in the question that the concentration is not given. Okay, the concentration is not given. You can see. Okay, so we need to eliminate the molarities. So molarity is going to get cancelled. Delta Tb by delta Tf equal to Kb by Kf, right? And what is delta Tb? Boiling point elevation of that solution. It is 0.18. That is given 0.18 into delta Tf, right? That is a freezing point depression. And Kb, yeah, Kb you need to write, this is Kf, okay? So 0.512 divided by how much? Yeah, 1.86. Is it clear? So you, with that
Yes.
you can, yeah, okay, with that you can find out the delta Tf value and how much are you getting? Yeah, you can simplify this delta Tf 0.18 into, you can cancel it by 2. You can, these data can get cancelled very easily. Okay, they are actually in line, very multiples of one another. So I think this is the calculation and D is the right answer. Okay, very good. So this is very simple question, but the language is little bit tricky, so you need to be very careful. But I hope you can do it. Okay, now let's move to the next question. Okay, so Hanifa, I hope you can hear my voice. And we were doing the qualitative property. Yeah. Am I audible? Yeah.
Yes, sir.
Okay. We were doing qualitative properties, freezing point depression. And this is the next question.
Yes, sir.
So, how many millimoles of sucrose should be dissolved to 500 gram of water to get a solution which has a difference of 103.57 between the boiling point and the freezing point? Okay, the boiling point will be increased and the freezing point will be decreased, and that will be the difference that you need to take, and that whole difference is actually 103.57. Here, so yeah, let's do it very quickly. I hope you can solve it. Very easy question, but the language again, sometimes you may feel that oh, this is a new question, but this is not a new question. The same question, but put up in a new way. Okay. So how many millimoles of sucrose you need to add it? Okay. Come on,
Sir, I
guys.
send the
Yeah. How much? Yeah,
sir,
Miraj.
750 millimoles.
C. Third option.
So 750 milli.
750 millimole. Okay. And Hanifa and Samara, are you getting the answers? Okay. Let's check it very quickly. Note down this thing. Yeah. Hanifa, how much you are getting?
Sir, I'm calculating.
Yeah. Okay. So solution which has a difference of 103.57. The difference between the boiling point and the freezing point. Okay. So let me take, it is water, so 0 and 100 is the boiling point. Okay, we can do some basic work. So this is 100 plus delta TB. Okay, yeah, and the freezing point depression, freezing point is somewhere lower. Okay, just lowered by delta T. So and delta TF, as we discussed in the last class, the delta TF is equal to the original freezing point, which was higher, okay, minus the new freezing point. TF naught is the original. Okay. And the difference between this, okay, this is TF, this is TF naught, okay, this is TB, this is TB naught, right? So you can take this difference. Sorry, this is TB naught. I wrote in a opposite manner. TB and TF difference you can take. Yeah. So let's check the answer quickly. Yeah, it is 750 millimoles. Good, Miraj. So yeah, what you did, tell me quickly how you solved this problem. Yeah, TF and TB, the difference between the boiling point, TB minus TF, right? That is 103.57. Okay, and this gap is actually 100 plus delta 100 plus delta TB plus delta T. Is it clear? Because 100 is the original gap between the freezing point and the boiling point of the water, and delta TB is increased, the boiling point is increased by delta TB, the freezing point is decreased by delta TF. So the complete gap after for the solution is going to be 100, the original gap plus delta TB plus delta TF. Okay, and it is equal to KB plus KF. Okay, right? So this value is already given. Okay, you can write it. Then I will express it. So this is 103.57, and 100 you can subtract. It is 3.57, right? Here, and you can
Yes,
write
sir. Yes, sir.
that. So I hope you did it in the same way.
Yes, sir. Same way.
Yeah, into molality. Good. So let's move to the next question. It is 750 millimoles. Okay. Yeah, and next let's discuss some osmosis. So osmosis, what is osmosis? Tell me quickly. Yeah,
Sir, sir, separating molecules through a semi-permeable membrane, sir. Sir, if sir molecules move from a higher concentration to a lower concentration, then so
yeah, good. So let me be little bit more precise. Okay, little bit more exact. Okay, so it is a movement of solvent molecule. Okay, from lower solute concentration to higher solute concentration. Okay, so here the solute concent. This is the sugar molecule. And these red colors molecules are the sugar molecule, and this is the water. The blue is the liquid. So the water moves from dilute to concentrated. Is it clear? So movement of solvent.
Yes.
Yeah, movement of solvent molecules from low solute concentration to higher solute concentration. It is because on this side, the water molecules are colliding with more frequency. Okay, on the semi-permeable, and this movement is to semi-permeable membrane, that also we need to discuss. Okay, so because if the solute concentration is less, and as per the kinetic theory, okay, these solvent molecules and the solid molecule, they continuously keep on moving and they keep on colliding the semi-permeable membrane. Clear? And you can see that water molecules are colliding more frequently on the semi-permeable membrane on this side, because here the sugar molecules are less and they are actually not blocking the water molecules to collide with the semi-permeable membrane. But on this side, you have less number of collisions of the water molecule to semi-permeable membrane. On this side, you have less number of water collisions. Okay, so water molecules are hitting more number where the solute is less, because the solute is not blocking the water molecules. They are not in much quantity. Okay, so water is going to move towards from left to right hand side. Okay, and there is an increase in pressure which is felt in the right hand compartment. Okay, and the level of the right hand compartment will be raised. So this phenomena is known as osmosis. You can see over here, this is also osmosis. Okay, so in this side, pure solvent, okay, means more collisions are there. You can see these yellow molecules. I hope you can see it very quickly. Okay, these yellow molecules, there are two molecules just for the sake of representation, and here there is only one. These are the solvent molecules. The solute molecules, these blue ones are very big. Okay, they cannot pass through the semi-permeable membrane, so they are hitting more strongly, right? So that's why the water is going to move towards this side. Okay, but uh, so the osmotic pressure is going to appear on this side, and it is represented by pi. Is it clear? So this is the movement of the solvent molecule through semi-permeable membrane from pure solvent side to the solution side, or from low solute concentration to the higher solute concentration side. And this movement will keep on rising the level of the solution towards the solution side. Okay, until and unless if the pressure exerted by the height of that raised column of the liquid stops the movement of further movement of this. Okay. So if suppose, let's say if after some time the height of the column stop rising and there is a difference of h. Okay, so the osmotic pressure pi equal to rho gh. Okay, you can measure it in terms of height also. Rho is the density of this sugar solution. That is into G into H. Because this raised column, okay, is actually just a second. I think there is some. This raised column is actually stopping the solvent molecules to get into the solution. Okay. So I hope this is clear. Everything. Example of osmosis as these are the examples. Okay.
Yes, sir.
Yeah. So blood cell. Okay. So suppose we get if our body get dehydrated immediately through injection, some or maybe some injection, they put some water into our body. Okay, but my dear students, the doctor can't put pure water into our body. Okay, why pure water can't be put through syringe into our body, through drip? Why we can't mix pure water into our blood? Yeah, Yeah. So what is
Sir,
injected?
the saline water.
Yeah. So yeah, saline solution is injected. Okay. And that saline solution is 0.9% NaCl. Okay. It is because it is isotonic with our blood. Hypertonic means the solution which is more concentrated than a given solution. Hypo is less concentrated. Okay. And isotonic means same. So if the two solutions are isotonic, there is not going to be any movement of the solvent. Means they have same osmotic pressure. So if we are putting a saline solution in our blood, that is 0.9% NaCl. Okay, our blood cells are going to remain stable. They are not neither going to get ruptured or they are not going to get imploded. Okay, so you can see over here. Suppose if you put pure water, if you put pure water into our blood, so these are the blood cells, as you can see, these round ones. They are more concentrated, and the water will get into the blood cells through their cell wall, which is a semi-permeable membrane, and they are going to get bulged just like raisins. Okay, when you put them in water. Okay, and they are going to burst. You can see over here. So if you put dilute solution, okay, dilute solution as compared to the concentration of the solution in the blood cells, okay, the solution will rupture the blood cell, that is hemolysis. While if you put more concentrated solution than this one, then what is going to happen? If you put more, all the blood cells are, the water is going to come out, okay, because the outside solution is more concentrated. Okay. So blood cells are going to shrink and they are going to die. Okay. So you put 0.9% NaCl, that is exactly the same osmotic pressure as that of our blood cells. So they remain stable, they don't die. Okay. So this is clear, right? And yeah, this pi, the calculation of osmotic pressure, pi equal to CRT, concentration. Okay, R is a gas constant. But what is the value of R which we'll take? Yeah, tell me, Mehraj, Samaira, in the calculation, what is the value of R which you are going to take? Yeah, in the calculation, R is having this gas constant. So pi is the osmotic pressure, which is also written as pi equal to CRT. The temperature should be in Kelvin. C is the concentration in mole per liter, that can be molarity. And what is R? What is the value? This is the gas constant, but it has having so many values. Which value are you going to choose? Yeah, Mehraj, tell me.
Sir, the question.
Yeah, what is the value of R? Which you
Sir,
are going to
8.3.
Yeah, 8.314 joule per Kelvin per mole. Yeah, the value of R which you said is correct, but that you are not going to put. That is a thermodynamics. It is used in thermodynamics wherever you will need to find a word. What we need to find over here, this is what pi. This is the osmotic pressure. So you need to put the value of R which is having the pressure in it. Is it clear?
Sir, R value will be different.
Yeah, liter atmosphere per Kelvin per mole. Is it clear? Whereas
Yes,
Samara and Hanifa, is it clear to both of
Yes.
you? Yeah, this is the common thing. If you need to calculate in bar, you need to put 0.083. Okay, it is almost nearly same. So you need to put, why we don't have to put that 8.314, because that is joule per Kelvin per mole. Okay, because we are dealing with the pressure, we are trying to find out the pressure. So we need to put the value of R in which there is a term for the pressure, unit for the pressure. Is that clear? So that is 0.081. So let's do our first problem of osmotic pressure. Yeah. Hmm. Which is so it is a colligative property. Let me tell you, it depends upon the number of solute particles and doesn't depend upon actual effective number of solute particles you need to count, and that is going to tell how much osmotic pressure is going to be there. Yeah. So C option, C is option second. Minimum
Press
osmotic.
and the answer.
Which one? C, third. This one. Okay. Hmm. So you need to find the so minimum osmotic pressure. Yeah.
Yes, sir.
Hmm. So just don't need to find the exact value. Okay.
Sir, C is the second.
Yeah, second option. Good. Yeah. C. Yeah. So just have the idea of this molarity, and but tell me what Samira and so but be careful, right? You need to look at the concentration. Okay. So where the concentration is less, just tell me. It is directly given. Okay. No need for the values of volume, as the concentration is directly given and it is minimum for glucose. So the minimum osmotic pressure is going to be for the glucose. Okay, C is the right option. Clear? Yeah. Okay. Is it clear, Samira, Hanifa?
Yes, sir.
Okay.
Yes, sir.
Yeah, what is the answer for this one? Three gram of glucose. Glucose has a molecular weight of 180, is dissolved in 60 gram of water at 15 degrees. The osmotic pressure is going to be felt on the solution side. Okay. And it depends upon the temperature. The higher the temperature, the higher will be the osmotic pressure. Okay. That you need to know. Hmm. Yeah. Tell me quickly what is going to be the answer. Yeah, Anifa. I didn't
Sir, I
hear
think
you.
it's C. C
Let's see.
6.57.
Okay. Mehraj and Samira, what you are getting? Anifa is getting the C answer. Okay. So let's check it quickly.
Sir, I'm getting D.
B, second option.
No, sir, D, fourth option.
Okay, fourth option. Let's check it quickly. So C option is correct. So pi equal to CRT. Mole per liter you need to find out. Okay, 3 by 180 are the number of moles. 3 by 180 is the number of mole of glucose. So 180 I will take it in denominator, 3 in numerator. And how much water is there? Okay, 60 ml. Okay, I have taken it 60 gram as 60 ml, right? Yes, so 60 by 1000 liter. So it is 3 by 180 by 0.06. Okay, this is the concentration, this is the R, and this is the temperature. That is 273 plus 18, so 288, right? So the answer is going to be option C. Clear? Okay. So let's, Samira, is it clear to you?
Yes, sir. Even I got the same answer.
Okay, very good. So let's move to the next question. So equal volumes of 0.1 molar urea and 0.1 molar. You took two. There are two solutions. The point it one has Mirage saying same osmotic pressure, yeah. And what about Samira and Hanifa? What they expect? Is the osmotic pressure of the final mixture, is it going to be more or is it going to be less? You take two solutions which have equal concentration, you put them together in equal volumes. Okay, what is the osmotic pressure of the final solution? The Mirage has already given the answer. Okay. Hanifa and Samara, you can also
Sir,
try.
I think it's option C.
Yeah, it is same concentration only, even after mixing, because you took same volume. So 0.1 more. Suppose if you take 1 liter, then urea 1 liter glucose. Okay. So both are 1 liter, and there is 1.1 mole, 0.1 mole. If you add them together, the 0.2 mole will be there of the solute, and it is a qualitative property. It doesn't depend upon whether it is urea or glucose. It just depend upon the number of solute particles. That's it. Okay, so 0.2 mole will be there, and the total volume will also be 2 liters. So the final solution is 0.2 by 2 liter. Again, the concentration is going to be same as that of the original concentration. So the osmotic pressure of the mixture is not going to change, right? So yeah, this is having the same osmotic pressure. And what about this one? Concentration in grams per liter of a solution of cane sugar, which is isotonic with a solution containing 6 gram of urea, whose molecular weight is 60 in 1 liter of solution. Miraj, yeah, good. Samara and Hanifa, what you are getting? Isotonic means
Is it
same.
correct?
Yeah, just find out. Just we will try to find out with you. You have given answer. Second,
Yes, sir. Yes,
yeah,
sir.
yeah, it's correct. Okay. So just look over it very quickly. C1 equal to C2 you need to do. No need to take RT, because the temperature and pressure, if they're not given, means they are at the same temperature and pressure. Okay. So what is the concentration of sugar solution? Okay, you have C mole per liter, but it is asked in grams. X gram per liter. Okay, and so the moles is X by 342 divided by 1. Okay, 342 is the molar mass into R into T, but R and T are going to come on the other side also, so they are going to get cancelled out. Anika, yeah, what you are getting?
I got 34.2.
Yeah, 34.2. This is 0.1 mole of urea you took, 6 by 60. That is directly 34.2. So now we are moving to a very, very important thing. So these are the normal colligative properties. Okay. Now we are moving towards the colligative property of electrolytes. Is it clear? So what are the things which we need to take? What are the precautions which we need to take if we are discussing? Till now we were discussing urea, sugar, glucose in all the examples. Okay. So those were non-electrolytic solutes. What it means, Samira, Miraj, Hanifa, non-electrolytic solutes. Means what? Non-electrolytic solute means what? Means they do not undergo.
Sir, they do not dissociate into ions.
They do not dissociate to ions. So if you are putting 1 mole, the particles are going to remain 1 mole. That's the guarantee if your solute is non-electrolytic. But there is actually a little bit we need to be careful if we are putting electrolytic solutes. Means the solutes which are going to undergo dissociation. Okay, like NaCl is there, KCl is there, many are there, acids are there. Okay, there are many of them which actually dissociate. Many salts which are soluble, they undergo dissociation upon putting in water. So you put 1 mole and you assume that okay, you put 1 mole in 1 liter, so the solution concentration is actually 1 molar, but actual concentration may change. It may actually increase. Suppose if the electrolyte is breaking into number of ions, more number of ions, or it may decrease also. Is sometimes what happens, the electrolyte molecules join together, okay, and they form a large molecule. Okay, under that condition also, the colligative property which was expected will be less than what you thought. Okay, so that you need to be very careful. So this is the example which is given in front of you. So 1 molar NaCl. Okay, this is 1 molar NaCl, and this is the, just if you don't know anything, you took only 1 mole, you calculated everything by 1 mole. Okay, this is the TF. Okay, KF into N. So this is the TF, but actually this is not the answer. This is not the observed colligative property. This is just the theoretically calculated colligative property based upon the ideal number of solute molecules. Okay, and the mistake here is you have not taken the association or dissociation. NaCl is undergoing dissociation, you have not taken that in account. But actually 100% dissociation is there if you take. So 1 mole NaCl is going to change to 2 moles, 1 Na and 1 Cl. So the particles are going to get doubled. So the colligative property which you need to calculate is twice 1.86 into 2. So the freezing point depression is going to be 3.72. Okay. And experimentally observed colligative property is actual. This is 3.72. Okay. Sorry, this is not 3. This is 3.4. Let me correct it a little bit. This is 3.4 actually. So because it may happen that you assume 100% dissociation, but it may not be 100%. Okay, if nothing is given, you can assume 100% for any, for a strong electrolyte. You can assume 100% without any worry. Strong electrolyte are NaCl, NaOH, HCl is strong acids, strong bases, soluble ions. Okay, they are strong electrolyte. So actually the thing is, for electrolytes, you need to take into account the actual number of particles due to association or dissociation. Okay, and that actual number of particles you need to calculate depending upon the formula, right? And that actual number of particles is indicated by the value I. This I is known as Van 't Hoff factor. Okay, so the colligative properties formula are going to remain same, which we discussed earlier. But actually, what happens is the formula remains same, but actually you need to take into account the actual number of particle after association or dissociation. You need to multiply those formulas by I. Okay, so these are the formulas which are there in front of you. The formulas are same, just there is an I inserted in these formula, because I will tell you how many times the particle will become depending upon the formula. For NaCl, the actual number of particles will be twice the actual number of particles. Suppose you took 1 mole of NaCl, the number of particles will be twice. Okay, and suppose you took ammonium sulfate. Okay, the I will be 3. So molality is the original moles of the complete compound which you put into the solvent. You multiply the formula by I to correct it to get the actual number of particles. Okay, and I you estimate by the formula. So you can see over here how to calculate I. So for strong electrolyte, you don't have to worry at all. For example, HCl I equal to 2. If nothing is given, you can take for strong electrolytes only. I am telling, not for weak. Okay, be careful. You can take I. So you can simply consider I by assuming the number of ions which are formed by one molecule or one formula unit. Magnesium sulfate, 2 ions are there. Magnesium chloride, 3 ions are there. One is magnesium, 2 is chloride. Okay, and assuming 100% dissociation, 100% dissociation. And if nothing is given, you can assume 100% dissociation. FeCl3 I will be equal to 4 because there is one Fe3 plus ion and the 3 Cl minus ion, so I will be equal to 4, and glucose I will be equal to 1. Is it clear? But if they give you some degree of dissociation, and that is required in terms of for weak electrolytes, okay, that you need for weak electrolytes where they are not going 100% dissociation and 100% association. So you can uh, have the formula like this. Alpha is the degree of dissociation or association which is given to you. Suppose there is a compound AB, okay, and alpha is the degree of dissociation, means it is not dissociating 100%. Let's say it is a weak acid. Okay, so it is 1 minus alpha, alpha, alpha. Okay, so alpha molecule, so out of 1 mole, okay, 1 mole per liter, but this is the degree, means out of 1 got dissociated and they formed one A plus and one B minus. So if alpha got dissociated, alpha A plus and alpha B minus will form. The total number of particles will be 1 minus alpha plus alpha plus alpha. Okay, so I is actually the observed number of particles, actual number of particles divided with by the original formula units which you put. Original formula unit which you put was 1 mole, let's say, but you put 1 mole, but after dissociating, the total particles will be these one minus alpha plus this. Okay, so it will be 1 plus alpha. So I equal to the observed number of particles divided by original formula unit which you put into the solution. Is it clear? Hanifa and Samira?
Yes, sir.
And if there is association, not only the particles undergo dissociation. Can you give me some example where the association is happening for acetic acid? Hanifa, can you give me some example of association of acetic acid? Yeah. Where it is happening? Suppose acetic acid, if you put it in water it will ionize, it will behave like an acid. So acetate and H plus, right?
Yes, sir.
So their I is going to be more than 1 because you have more than 1 particles after dissociation. But if you put it in benzene, which is a non-polar solvent, so in non-polar solvents, what may happen is the acetic acid molecule, Samira, the 2 molecules, instead of losing their H plus, they may come together and they may combine together by hydrogen bond, like this. Okay, so this is the dimerization, but you don't know whether it is forming a dimer or trimer. Okay, it is given in the question and depends upon the nature of the molecule. Normally dimer is the most common, but in this case we have assumed that the n molecules join together. Let's say you have put some molecules, 1 mole of molecules, and if 2 molecules join together, the final number of particle will be half. If 3 molecules combine together to form one unit, the final number of particles will be 1/3. So here I've given general formula in which the n number of particles are combining together to form an. Is it clear? So 1 minus alpha. Okay. So whatever is coming out from here, so alpha reacting, not reacting, actually associating. That is a more correct one. So what is left? 1 minus alpha, and what is formed? Alpha by n. They will become 1 upon n times. Suppose if dimerization is there, so it is half time. Okay. If trimer 3 molecules are joining together, so if you put 1 mole, they will become 1/3. Okay. If n molecules are joining together, so if you put 1, if alpha is undergoing association, so they will be alpha by n. So observed number of particles will be 1 minus alpha plus the associated particles alpha by n upon original formula units which you put, that is 1. So this is the value of I. I gives you the total number of particles divided by original number of particles. And if the formula is like this, if there is a dissociation, this is going to be the right. So so I hope you can calculate alpha. Okay. Yeah, Miraj. And I can be found out by number of particles. Okay. So actual number of particles divided by number of moles of the formula units which you put, actual formula units which you put. Number of mole of the formula units. Like 1 mole of NaCl, so this is going to be 1 and this is going to be 2. For barium chloride, BaCl2, if you could put 1 mole, so this is going to be 1, but this is going to be 3 because they are forming 3 ions, 1 barium, 2 chloride. Okay, but if you have colligative property given, let's say boiling point elevation is given. So this one is the boiling point elevation. Okay, just Kb into n without taking into consideration of association or dissociation. That is normal colligative property, means it is the colligative property which you consider without association or dissociation, and this is the experimentally observed colligative property, which is actually the value of the colligative property, same colligative property, if you consider association and dissociation of ions. So which formula you need to put? Do you need to put this one or do you need to this one? That your question will tell you. Okay. So what is there in the question? That you can see. Okay. Or sometimes what happens is the molar mass is also going to get affected, because these colligative properties are even you use them to calculate the molar mass. Okay. So if there is a dissociation happening, if the particles are dissociating, so the molar mass is going to be less. Okay, because the same mass is divided into a number of particles, so the molar mass, okay, is going to be less than what was assumed. Okay, what was calculated as per the formula. Okay. But if you have the molar, if there is an association together, the molar mass which you calculate for that from the formula, you get it for the associated value, okay, associated molecule, you are going to get higher molar mass. So if you, let's say, I will give you one example. Suppose if you assume 100% association for acetic acid, what's going to be the molar mass? Yeah, Miraj, Hanifa, Samaira, can you tell me? If you assume 100% association for acetic acid, what's going to be its molar mass? What is the original molar mass of acetic acid? That is 60. Okay. And if you assume 100% association, means all the molecules which they join together to form a dimer, the molar mass which you get will be 120. It will be just the twice of the molar mass of the single unit. Is it clear? Because they join together.
Yes, sir.
So that is actually abnormal molar mass. That is not the real molar mass. You are estimating more if the particles are getting associated, or if the particles are getting dissociated, you are estimating less. Okay, so if the molar masses are given, then you need to calculate the I value, Vento factor by this. Okay, normal molar mass. So I is directly proportional to number of particles. So you have that number of particles, actual number of particles after association and dissociation in the denominator, divided by original number of solute particle which you put into the solution. And I is directly proportional to the colligative property. So actually experimentally observed colligative property, the real value of the colligative property which you are observing, divided by the original colligative property which you calculated or assumed by without assuming any uh, association or dissociation. But I is inversely proportional to molar mass. Okay, so here the observed value is at the bottom. Everywhere the observed value is at the top. You can look in the numerator. Okay, so observed molar mass I is inversely proportional to the molar mass. Okay, so observed molar mass is in the denominator and the original molar mass is in the numerator. Okay, so you can get the question in any manner, but it is very simple, but still students get confused. Okay, so you need to be careful regarding this. Okay, so these are the modified formulas. By taking I into account, you multiply all the formulas, all the colligative property by I, so that you can get the value of actual value of colligative property. So this is the first question, which is a very basic question. So assuming 100% dissociation, what are the values of I for barium hydroxide, BOSO twice, for C6H12O6, that is glucose, for potassium phosphate, K3PO4, and for nitric acid, HNO3? Yeah. What's going to be the answer? Samaira, Anifa, quickly tell me. Very basic. Mehraj. Hmm. Mehraj is telling, Hanifa is telling B. Hanifa, just check it little bit. You are very close to the right answer. Just check it once again. Samara, what could be the answer as per you?
Sir, I think it's C.
C, yes. C is the right answer. So this is going to form a barium ion and 2 hydroxide ion. And this is going to form a glucose. This is going to form 3 potassium ions and a phosphate ion. And this is going to form, this is HNO3, and we know it is a very famous acid, so HNO3. So this is getting dissociated into 3 particles. This is not dissociating. This is dissociating into 4 ions, and this is dissociating into 2 ions. Assuming 100% dissociation, because ideal Vento value means you are assuming 100% dissociation, because these are strong electrons. So 3142 is the right answer. Right? Correct? Okay. So let's move to the next question. Very simple question. Just you need to be very careful, but actually you need to be very careful while doing these questions of Vento factor. They are very simple, but caution is required, okay? Because it can go wrong. Yeah. So which observation or observations reflect colligative property? Okay, which is in line with the colligative property, right? You need to tell me. Hmm. So which reflect colligative property? What are the things mentioned over here are colligative property, are due to the colligative properties. Okay, means because they are because of the number of ions. Yeah, Miraj, Hanifa, any idea? Samara, just help me to get the answer quickly. What could be the answer? Yeah, I hope all of you can do it quickly. Miraj, any idea what you are doing? Tell me quickly. Hanifa, Samara, what could be the answer? So which observation or observation are due to colligative property? Yeah, yeah, Hanifa, tell me.
I'm not sure.
Okay, yeah. So colligative property, suppose if you put a solute and there is some change in the property of the pure solvent. There's change in the physical property of the pure solvent. That is a colligative property which is due to solute particles. That is colligative property. But you can't have a colligative property for pure solvent, just for a pure solvent. Means if you do not have any mixing of solution, you're not if you're not putting any solute particles and all, means that is not the discussion related to colligative property, right? That's the hint. Okay, so zero point 0.5 molar NaBr has higher vapor pressure, and 0.5 molar barium chloride is having lower vapor pressure. Yeah, that's true, because barium chloride is going to dissociate more, though the number of formula units which you took are same, but barium chloride is going to give you 3 ions, and those ions are going to cover up the surface of the solvent, and those ions are going to hinder the release of solvent molecules. So the vapor pressure is less for barium chloride and it is more for NABR. And the difference in the vapor pressure, in spite of the same for number of formula unit, the difference in the vapor pressure is due to the effective number of ions which are formed after dissociation. So that is a colligative property. Is it clear, Samara?
Yes, sir.
It is a colligative property. Okay. No, the next thing is 0.5 molar NaOH solution freezes at lower temperature than the pure water. Yeah, you are talking about a colligative property because it is a freezing point depression of the NaOH solution. Okay, due to the addition of NaOH solute, yeah, it is a colligative property. And Mirage pure water freezes at higher temperature and pure methanol freezes at some another temperature. That is due to intermolecular forces. These are the pure solvents. Okay, two different pure solvents. These are not solutions. Okay, so this is not a colligative property. We are not talking about the colligative property in this case. So yeah, which observation reflect colligative property? The right answer is going to be the option first. Is it clear to all of you?
Yes, sir.
Okay, very good. So that's how you need to think. Okay, yeah. So this is another very basic question, just kind of warm-up exercise for winter factor. Tell me what's going to be the answer. Aluminum phosphate is 100% ionized, and it's the original concentration of the formula units which you put as 0.01 molar in aqueous solution. Okay, what is the value of delta TB by kV? Yeah, tell me. Delta TB by kV. What's going to be the value of delta TB by kV? Yeah, guys. Good. Yeah, Miraj, what happened? Samira and Anifa, what's going to be the right answer? Yeah.
0.02.
Option 0.02. Yeah, correct.
Yeah.
Yeah. Yeah. So delta TB, the boiling point elevation by mole boiling point elevation constant, molar etioscopic constant is equal to molality. But that is the molality if your electrolyte, if your solute is non-electrolytic, means it is not associating or dissociating into ions. But if you have taken a solute which is undergoing association or dissociation, in order to take it into account the association or dissociation, you need to multiply it by I. So aluminum phosphate, aluminum is +3 and the phosphate is -3, and they have two ions. So I will be equal to 2 if you assume that it is 100% dissociated, so 2 into 0.02. Right, so that is going to be the answer. Right. Good. And what about this one? This again is a very simple, very basic question. Here the I is already given. For barium nitrate, what is the value of I which you can expect? If nothing is given, what is the value of I which you need to take? For barium nitrate. Yes, Amira, tell me. What is the value of I which you can take for barium nitrate? It is going to be, is it 2 or 3? Hanifa and Miraj, the value of I for barium nitrate, it is going to be 3, because there is one barium ion and two nitrate ions, total 3 ions are going to be. But that 3 value is going to come up only if it is 100% dissociated, then only it is 3. Okay. But if it is not 100% dissociated, it is not 3. Some of the barium nitrate are as it is, some of them dissociate into 3, but the total number of particles overall will not be the 3 times, because some of them remain as it is. Okay, so the new value of I is 2.74. Now the question is saying that you need to calculate the degree of dissociation. You need to tell me out of 1 mole how many are dissociated. Clear? Hanifa, Miraj, Samira, sorry. Yeah, tell me.
Yes, sir. I
Yeah,
got 87%.
87%. Yeah, 87%. So you can write the equation as you used to do it in,
Yes, sir.
yeah, in ionic equilibrium. You can write it like this. You can assume the degree of dissociation to be alpha, means out of 1 alpha got dissociated, this is alpha and this is 2 alpha. The total number of particles will be 1 minus alpha plus 2 alpha, right? So it is going to be 1 plus 2 alpha. And the original number of particles which you put is 1. Okay, and it is I. So I is 2.74, it is given. You can calculate alpha 1.74 by 2. Alpha is 0.87. Yeah. 87. So alpha is out of 1, so that is 87% dissociated. Okay. So this is the way to do this question. I hope it is clear. Miraz, Samara, is it clear?
Yes, sir.
Okay, very good. So let's do this next question. So which is the next topic should we start? Tell me in the next class. Should we do solid state or should we go for organic? Yeah, tell me. Okay. So let's do this question first quickly because the time is running out. We just have 5 more minutes. We can do this question. So 20 gram of naphthoic acid is there. This is the solute. It is dissolved in 50 gram of benzene, which is the solvent. The freezing point depression is 2K. It is the observed freezing point. Okay, by considering the dissociation of the naphthoic acid. So delta freezing point depression, delta TF is equal to I into KF into molality. Right? Yeah, delta TF into I into KF into molality. Yeah. Tell me quickly, what is the value of I? Naphthoic acid moles you can calculate. But for in order to get the moles, you need to calculate the molar mass, and it is the formula is very big. 11 carbon, okay, 8 hydrogen, and 2 oxygen. Okay, so this is the naphthoic acid. The formula is. You don't have to know the need to know the structure. Just I'm writing. So what is the molar mass? 11 into 12, 132 plus 8 plus 32, 164 plus 8. That is 172 is the molar mass of this. So how many moles you took? Delta T of freezing point depression is 2 into I into KF. KF is how much? KF is 1.72 into molarity is how much? 20 divided by molar mass 172 into how much? Into 50 gram of benzene. You need to take the mass to of the solvent to calculate the molality by 1000, right? So how much is it going to be? So this is 1 by 100. Okay, and this is 100 and this is 100. This is cancelled, this is cancelled, this is cancelled. Okay, and 5 into 4, right? So I is equal to half. That's what you are getting. Is it clear? Yeah, so that is half. So I hope this is clear. Samara and Miraj.
Yes, yes, yes.
So yeah, this is the numericals related to the vendor factor. Now tell me, what should we start from the next time for questions? You can, what's going on, what you need to do, okay, you can tell me, you can share it with me. Yeah. Miraj, tell me, should we start with alkyl halides, aryl halides?
Yes, sir.
Okay, we can do that, not a problem. Yeah. Okay. So this is the thing, and let's keep in mind the small things which I told you. Okay, where you can go wrong. Very simple. Or if you want, we can do